Thanksgiving is a particularly busy shopping weekend in the US. Also known as Black Friday, Cyber Monday, or BFCM, it's becoming increasingly popular in other countries as well. And over BFCM 2020, Shopify merchants made sales for more than 5 billion USD, with peak sales over 100 million USD per hour. So for us at Shopify, even the shortest downtime matters, and high availability of our application is key. Today, I'm going to compare different approaches to offload work and how they can help us to ensure high availability while keeping our overall code base as simple as possible. I'm going to start with a brief introduction about high availability and offloading work. I will talk about background jobs, features they provide, but also the challenges they might pose, and how we're using them at Shopify to ensure high availability of one of the largest running Rails applications. I'm comparing background jobs to message-oriented middleware like RabbitMQ and event logs like Kafka. So what is high availability? Availability is much more than just uptime. The user needs to be able to interact with the system. And just telling them to come back later is not good enough. So we're talking about a somewhat meaningful interaction. And not just for one individual user, but for all of them. Availability is considered high if this holds true whenever the users need it to be. So for our application to have high availability, it needs to be able to accept incoming requests. More specifically, the user-facing part of the system has to be able to do that. If the same part of the system is doing all the heavy lifting related to processing the requests, it might become overwhelmed and too busy to accept more requests. That's why we like to move work away from the user-facing part of the system into the back whenever possible, which means whenever it's something that can be done outside of the main request response cycle. And in the Ruby world, background jobs are a pretty popular way to offload work into the back. Rescue and Sidekick are widely used background job backends. And a background job is a unit of work to be done later in the future. The application server forks a worker for running the job, and this can even be on a different machine. But the two of them have to communicate, for example, in order to address failures. On the other hand, the application server shouldn't have to wait for the worker to finish its task. So we need some kind of asynchronous communication between application server and worker. We can facilitate that by placing a message queue in between them. Senders and receivers of messages can interact with the queue independently at different times. And the message is the task to be done by the worker. So we're also calling this queue a task queue. The application server doesn't have to wait for the worker to process the message. And we can set up several workers to work on several tasks at the same time. And this is the core of a background job backend. It's a task queue along with a bit of broker code for managing the workers. It's encapsulating the asynchronous communication between application server and workers, which allows us to keep our own background job code very simple because it's simply not aware of being run in the future. Shopify is queuing tens of thousands of jobs per second. And we're using them for a broad spectrum of use cases, like firing webhooks or purchasing shipping labels. So what are the features that are making background jobs so attractive? Background jobs decouple the user-facing request, which is served by the application server, from any time-consuming backend task done by a worker. And this is improving the response times. But whatever improves one user's response time also improves availability for other users. Shopify is facing traffic spikes, sometimes going up to 170K requests per second. But a sudden spike in, say, image uploads is not going to hurt us if the actual image processing is done by a background job. Our queue might grow, but the speed of queuing more jobs is not constrained by the speed of processing them. So the users can interact with the application as fast as usual. Our message queue is a buffer, and this is giving us high availability even when facing unpredictable traffic. When dealing with large tasks, we can split it into a number of subtasks and queue them as individual background jobs. If we set up multiple workers, we can have them work on these subtasks in parallel at the same time. Our code, again, is super simple because it's not aware of being run in parallel. All it needs to know is how to handle one of these subtasks at a time. When a worker encounters an error running the job, it's requeuing the job so that the job is retried again later. Again, our own background job code is not aware of this. It remains very simple. All of this is encapsulated into our background job backend. And since all of this error handling is happening in the back, it's also not affecting the availability or the response times of our user-facing application server. So the background job backend encapsulates the asynchronous communication between application server and worker, but it doesn't really change the fact that it is asynchronous communication. So we're still facing some challenges here. The application server queuing the job and the worker processing it might run different versions of a code base, for example, during deployments. And if we're doing canary deployments, the period of time where we might face different versions can be pretty significant. So changes to the job parameters can actually break our application. A job might be queued with the new parameters, but processed on a worker expecting the old ones, or vice versa. So breaking changes to job parameters need to roll out through a sequence of changes, preserving backwards compatibility until all legacy jobs from the queue have been processed. Whenever a job succeeds, the worker confirms that it is safe to remove this job from the queue. But what do we do if a job is not confirmed in time? We can allow a second worker to pick up this job and run it. But if our first worker did not crash, it's simply a little bit slower than expected, our job is going to run twice. On the other hand, if we do not allow a second worker to pick up the unconfirmed job, and our first worker has crashed, our job is not running at all. So we have to choose between at least and at most once delivery. And at most once delivery is great if running the job twice is worse than not running it at all. But very often, this points to some kind of flaw in our code. For example, if we are worried about charging a customer twice, we could carefully track all charges we are making and check that state before any attempt to make a charge. This makes our background job idempotent and allows us to safely opt for at least once delivery. Our job queue is most likely persisted in a different data store than our operational data. For example, the operational data might be in MySQL, while the job queue is in Redis. And that means queuing our job is not part of any enclosing database transaction. If we still queue it from within that, our job might be processed before the enclosing transaction is committed, or even in case the enclosing transaction loads back. And that means our job may not have the data available that it needs. So we should commit the data before queuing the job, but there's still a risk here. Our system might crash after committing the database transaction and before queuing the job. So this job will never run, and our system is left in an inconsistent state. We can address this by not queuing the job right away, but writing the job parameters into a staging table that is in our main data store. So this can be part of an enclosing database transaction, and a scheduler can drop by, check the staging table, and queue the jobs accordingly. It also reports back when it has successfully queued the job. So this guarantees our job is queued. But we're still spreading out our database rights between application server and several workers. So we're basically dealing with multiple local transactions. And when the last job related to our task succeeds, the last local transaction commits, we are eventually reaching consistency. But some of our jobs might fail, and that would leave our system in an inconsistent state. We can address this by applying a pattern called Saga, more specifically, its command orchestrator pattern. That basically means a job is reporting back to the staging table when it has completed successfully. A scheduler checking that staging table can spot inconsistencies and make sure they are addressed. Our jobs leave the queue in a predefined order, but they end up with different workers, and we're not able to predict which worker is going to work faster. And if a job encounters an error, it's going to be requeued and processed much later. So if a job depends on another job having finished, queuing both of them right away might result in them running in the wrong order. But the first job, when finishing its task, could queue the second one as a follow-up to make sure they always run in the correct order. This is sometimes considered a different flavor of the Saga pattern that is called events choreography. It is very easy to build this, but it can be pretty hard to debug the system. We're basically pushing all our problems down a potentially very long chain of jobs queuing jobs queuing jobs. If we prefer to avoid that, we can resort to the command orchestrator flavor of the Saga pattern, which avoids this problem, but is a lot heavier to implement in the first place. A background job doesn't have to be as fast as a user-facing request, but long-running jobs still create some problems. Rescue, for example, prevents workers from being shut down while a job is running. That means we cannot deploy this worker. And it's also not very cloud-friendly, because in the cloud, our resources may not be available for a long time in a row. Sidekick behaves a little bit nicer. It's aborting and requeuing a job when we're attempting to shut down the worker. But still, our job may not finish before being aborted again. If we're deploying faster than our job can complete, the job will never succeed. And with a core of Shopify deploying about 40 times a day on average, that's not an academic discussion. It was an actual problem that we needed to address. Luckily, most long-running jobs are singular in nature. They are iterating over large collections of data. So we're splitting our job into the collection to iterate over and the task to be done on each iteration. We're setting a checkpoint after an iteration and requeue the job. Next time the job is taken from the queue and the processing is going to pick up at the checkpoint. So we end up having interruptible jobs with automatic resuming. We can shut down our workers anytime, which also means we can deploy as often as we want to. And if, for example, our database is struggling, we can throttle jobs or back them off completely, preventing the jobs from making any ongoing incident worse. If we need to move data around between different database shards, we can safely do so by interrupting any job that's currently running. Our job iteration framework is open source. You can find it on GitHub. We could reach some of these results by splitting the job into subtasks and queuing them independently. But keeping everything in one job allows us to fully leverage the regular retry mechanisms, and it makes it much easier to track success or failure for the overall task, because a resume is not a retry. We're basically encapsulating these scaling issues into a separate abstraction layer, and that again allows us to keep our concrete background job classes very simple. Our background job backend is a Ruby gem that is running on application server and worker. The task to be done is an instance of some background job class, so it's a Ruby object that we're passing around here. This means both application server and worker need to implement this class. So background jobs are great for offloading work to a worker that is running the same code base as the application server. In other words, a monolithic architecture. To sum it up, background jobs are based on task queues. They can make our overall system a little bit more complex due to the asynchronous communication involved and the lack of guarantees that comes with it. But by abstracting this complexity away and individual jobs not being aware of being run in the future, we are able to keep our concrete background job classes very, very simple. And background jobs are great for monoliths because that's where application server and worker are running the same code base. But if I would like to extract, for example, image processing into a separate microservice, maybe one that's not even written in Ruby, I need a different way to communicate with this service. And that is where message-oriented middleware can be useful. Message-oriented middleware can be based on several different protocols, and there is a number of different implementations around. RabbitMQ is a pretty popular one. And in the end, message-oriented middleware is also mostly based on task queues. But the logic for message routing and managing workers is now in our middleware. It's completely separate from our services. We are no longer passing Ruby objects around. Message producers and message consumers agree on a purely database interface, something like a JSON payload maybe. And that means each service can easily be replaced with a new, different implementation, even if that implementation is based on an entirely different technology. All it has to do is adhere to our database interface. By using task queues, the message-oriented middleware brings many of the features of background jobs to a distributed microservices architecture. Since I'm not really working with that technology at Shopify, I made up an example to illustrate how this works. So think about a business partner going out of business. That clearly is an update to their data in the business partner's microservice. But we also might want to cancel their pending orders or put their support contracts on hold. So some other services need to learn about our business partner being broke. Message-oriented middleware can be used to broadcast that information. The business partner's microservice can produce a message about it that the client services consume. If a message consumer is temporarily down, the message stays in the queue until the message consumer is back and can continue processing messages. So no information is getting lost over a temporary downtime. The message producer drops the message into the queue and immediately moves on. So it's not affected by the message consumer's downtime at all. And this is helping us to ensure high availability of our message producer, which often is a user-facing application server. All of this is encapsulated into the broker, the messaging middleware. So our concrete message consumer code is not aware of it and remains very, very simple. Message-oriented middleware usually does not simply use a single point-to-point queue. It's using topics. In RabbitMQ, that means every message consumer has its own set of queues, and the middleware duplicates the messages into the right queues. So in difference to HTTP, we are not restricted to one-to-one routing, and the topic is giving us publish-subscribe capabilities. A new service can subscribe itself to the messages it's interested in by creating its own queues, and the message producer does not need to know anything about the new consumer. This is a different made-up example where a number of microservices send a warning message whenever they observe something suspicious, and a message consumer aggregates all these messages into a fraud score. In this case, a new message producer can add itself to the system and start issuing these messages, and the message consumer doesn't need to know anything about this new message producer. Since message producers and message consumers don't even know about each other's existence, failures of one service have very little impact on other services, and that helps us to improve the availability of our overall system. Again, leveraging these features can pose some challenges. Similar to background jobs, we're dealing with queues, and that gives us a lack of delivery, consistency, and order guarantees that we need to address. Designing our messages basically means designing the database interface between message producer and message consumer. So we have to think about versioning, breaking changes, and so on. In the examples I provided, we routed messages from one producer to several consumers, or several producers to one consumer. Now, technically, we can also route messages end-to-end, but that's really making breaking changes difficult because we have to coordinate them between several producers and several consumers at the same time. And in my experience, our business domain is usually modeled much more accurately by using several different messages, some routed one-to-N, others routed N-to-1, instead of having this one super message covering everything. Background jobs are essentially commands. Process this image, send this email. So in a microservices architecture, we could replace that with command messages, maybe sending a message to the email service to make sure it sends a welcome email to a new user. But that means our message producer needs to know about message consumers and what they are supposed to do with the information we're sending them. That's an unfortunate coupling, but we can use different semantics to basically achieve the same thing, which is sending a welcome email. We can send out events that are propagating information about something that has already happened. In the example, we could produce an event stating that a new user has signed up. All services interested in that information can subscribe to this message. And one of these message consumers would be our email service sending out the welcome email. But our services are nicely decoupled here. The message producer doesn't know what the consumer is going to do with the information about a new user signing up. And the knowledge about welcome emails is kept local inside the email service where it belongs. there's different flavors of event messages that we can send. If a user updates the same information several times in a row, the last message the service receives about this is not necessarily from the most recent update, because our messages might be out of order. That doesn't hurt if the messages are commutative. If our payload only contains, say, the user ID of the updated account, the payloads of all these messages are the same, and the order doesn't really matter. Now, an ID is enough for something like cache invalidation, but for many use cases, the consumer will have to fetch the updated data from the message producer owning the data, and this can be quite a bit of traffic. In addition, the message consumer does not end up having the full history of states. It only learns the state of, say, the account at the time of fetching the latest data, but might have missed some updates that happened in between. This is different for event-carried state transfer, where the payload contains all the updated data. This means the message consumer never has to fetch data from the message producer, and it also has a full history of all these changes. However, the consumer is now responsible for accounting for out-of-order delivery. Sometimes that can be as simple as looking at an updated timestamp, but it is now the responsibility of the message consumer. As Rails developers, we are mostly shying away from fat controllers. So in return, we gravitate towards our active record models. There certainly is a temptation to fire our event notifications from active record callbacks. But if we center our thinking around active record models, we can easily end up leaking implementation details of the message producer. A message consumer doesn't really care about a field in the producer's database being modified. In fact, it shouldn't even know this field exists. That's an implementation detail of the message producer. Similarly, our users don't want to update fields in databases either. They want to accomplish some real-life task, something in their business domain. And that is reflected in our business logic, not in our persistence layer. So we can avoid the risk of leaking implementation details by focusing on events in the business domain and firing our events from within our business logic, not from the active record models. Messages are removed after consumption. That means we are not able to replay the stream of messages. And each service kind of lives in its own reality. That's great because they're highly decoupled now. But while a service might be the source of truth for a particular piece of data, we are not having a single source of truth for the state of the overall system. That can be a challenge for debugging, and it also makes it very hard to do something like event sourcing. So message-oriented middleware allows us to offload work into highly decoupled microservices. That decoupling is great for high availability, but it leaves us without the notion of a system-wide state. To sum it up, message-oriented middleware is based on queues and topics. It can make our overall system a bit more complex because we're again dealing with asynchronous communication and the lack of guarantees that comes with it. But by abstracting away into the middleware that individual messages are consumed in the future, and also abstracting away the complexity of PubSub, it allows us to build very simple, concrete message consumers. This makes message-oriented middleware a great fit for decoupled microservices, but it leaves us without the notion of a system-wide state, so we don't really have a source of truth for event sourcing. Event logs are approaching event messages entirely different. The most famous one is probably Kafka. And the events are persisted into an append-only log. All consumers share this one log and can read from it whenever they want to. So our broker is stateless. It does not track event consumption, and there is no queues. With a stateless broker and append-only writes, we are getting an incredibly high throughput. This is great for high availability, and it's an awesome fit for real-time applications and data streaming. Our events are not removed after processing. So we actually can replay the stream of events as often as we want to, which makes a great source for event sourcing. So event logs are a great way to offload work into microservices while actually keeping the notion of a system-wide state around. To sum it up, event logs are based on a shared log. There are no queues. They might make our overall system more complex because we're still dealing with asynchronous communication. And our event consumers might also be a little bit more complex because they're stateful. They need to track their own event consumption. In return, we're gaining a single source of truth that we can leverage, for example, for event sourcing. And event logs are a great fit for high throughput applications. To sum it up, background jobs are based on queues, and they're a great fit for a monolithic architecture. Message-oriented middleware is based on topics and queues, and it's awesome for decoupled microservices. While event logs use a shared log, there are no queues, and they are an amazing fit for event sourcing and high throughput applications. Shopify is writing several million Kafka messages per second. This is a recording of a Kafka-powered real-time visualization of Shopify merchants making sales over BFCM 2020, with every particle representing a real order. Thanks for listening.